Good afternoon. I'm Dr. Nakashima, Principal Investigator of WPI I²CNER. And thank you for coming this seminar today. So today we have very special guest from Tokyo, Professor IIJIMA. I know he is widely well known, very famous professor. So I understand you know quite well, but let me introduce his background and career very briefly. In 1982, yeah, he was in after getting PhD in Tokyo University. He moved to Arizona State University, and where he developed high-resolution transmission electron microscopy. In 1982, he returned to Japan and worked for 5 years on an ELATO project on nanoparticles, then joined the NEC Fundamental Research Laboratories. In 1991, as you know, he discovered carbon nanotube, and first paper published in Nature. And citation of his first paper in Nature is over 10,000. That's an amazing number. Just one paper. And following the discovery, he has been honored with numerous awards, including Franklin Medal in Physics, 2001, and Agilent European Award, 2002, Balzan Prize, 2007, Italy and Switzerland, Calvi Prize, Norway, 3 years ago, Prince of Asturias Award, Spain, 3 years ago, Order of Culture, Japan, 2 years ago, and yeah, and more. And he is now a member of Foreign Associate of National Academy of Science and Norway Academy of Science and Lecture. And also he is a member of Japan Academy. So today it's my great pleasure to chair his special lecture. And the title of his talk today is Electron Microscopy and Nano-carbon Materials. Professor IIJIMA, please.
Okay, thank you very much. I had some slight catch a cold, so my voice is something strange. Anyway, it's I'm very happy to be here, and Nakashima Sensei invited me to this, I think, the prestigious lectureship. Anyway, this is my first visit to this campus. Actually, a week ago, I was in the other campus of Kyushu University, and I gave a similar presentation in a small audience. Anyway, so that's my title. Okay, so this is my recipe. What I'm going to do now, my title is slightly maybe different than what I thought when I had this the invitation. Content is not only electron microscopy, but some other stuff I'm going to say. What is the carbon nanotube? So this is my sort of present the interest. So I like to speak about this first. Then the more general, particularly young students. And then I like talk about the science. Start with seeing carefully. So maybe you don't understand, but see what I'm going to say. Then somehow related to this the subject, my teachers who taught me the importance of seeing. Okay, so seeing means I'm thinking of the electron microscope, seeing the many things. Then coming back to the discovery of carbon nanotube and that state of art of TM research. So I'd like to speak about the latest our result. Okay, so no, this way. Right. So I started with this. That's the electron micrograph of single wall carbon nanotube. It was mixed up again. Sorry. This one is a single wall carbon nanotube. So this one was published in 1993. And anyways, these are sort of the carbon nanotube. Then yes, that was nearly 18 years ago. All the pictures, but this one is quite young, probably a couple of years ago. We had this one, 2007. Okay. Then see this one. Yeah. So from this kind of electron micrograph, you can immediately determine what atomic structures of this carbon nanotube. For instance, this one. I think you are familiar with the carbon nanotube. Green balls are the carbon atoms. Then if you round up, then you can have this cylindrical structure. And then also you can have this side different structure. Now this time we have the chiral structure. So all days, some years ago, to know these structures, you have to do a lot of the analysis. But these days, we can have these nice images, so we can tell what atomic structure, what the diameters, what the defects are. So now all the new carbon material, just to remind you what type of carbon materials we have so far. Yellow one is the conventional. All we are familiar with this the carbon fibers, tungsten, diamond, graphite, Sumio charcoal. Then these are meant to be the new type of carbon material. So I started with the C60 fluorine, carbon nanotubes, nano horns, and the mesoporous carbon. Then nano diamonds. Then the graphene, of course. Last year, the Nobel laureate, Nobel Prize given to those who find this one. Anyway, so we are. Let me see. Right. So this is again the sort of the introduction of new type of carbon material. Yeah. So this is of course graphite, naturally formed. Then fluorine, the carbon nanotube. Then the graphene. Yeah, graphenes, and then like so. All right. So we know all this now. Then particularly when you talk about this kind of new material, if you're a student, you go to the textbook, okay? Then you try to find the phase diagram of carbon, for instance. So this is the phase diagram of carbon. That's the point is as long as you look at this phase diagram of carbon, there's no fluorine, no nanotube, no graphene, but we have this new material. So don't stick on this the old sort of textbook much. Otherwise, you cannot find a new material. So this is a very important message. So in the phase diagram, all you can find is the diamond, amorphous carbon, or graphite. Right. Okay. So that's then nanoscience and nanotechnology. The next slide is prepared for high school students. So sorry about this. But in order to explain the nanoscience, what is it? So I had this normal copper wire. Okay, and then nanowire, like this. So then we try to run the current through these wires. What happened? I think our image something like that. You know, that's the electron goes through this the wire. What about the down this one? So because there's only this is they can do. So the two are quite different. And indeed, if you do the theoretical constellation and others, then we see this. Then similarly, the carbon nanotube very close to this one, okay? And then also the graphene has similar structure than this. And so all these showed us very nice, interesting the properties, the physical, chemical, mechanical, and so on. Now, probably you laugh at this kind of cartoon manga, okay? But this is real. I think this is the what I show you in the previous cartoon. Right. Okay. So what is this? This is the I repeat again. Okay. So material is graphene, and then they disappeared. Okay. So what happened in here is this one. Then if you etch away the carbon atoms, then what you can have at the end like this. That is what have you seen in the previous slide. So it's not a joke. You know, I show you this the chain of carbon atoms. So if you're interested in, you can do the transport experiment which use this carbon single atom chains. Okay, so yeah, this is like that. Unfortunately, we don't see the individual carbon atoms in that thread in the string. So if you're a chemist, then maybe double this connection of the carbon atoms, or maybe triple single. But from this experiment, you cannot tell which one which. All right. So then this is just I tried to show you when you talk about the nanoscience, these things are quite the interesting, unique. Okay, so then the growth of carbon nanotube using catalyst. Then yes, so top one. Let me go back. Right. So in order to grow the carbon nanotube CNT, then we have the carbon vapor, or then also simultaneously we have the metal vapor. Then if you cool down the system, then we started to have this carbon nanotube grown from the metal particles and so on. So this is gas phase reaction, but also you can go to the substrate. You can use a substrate like this. Similarly, we have the metal atoms deposited on the surface. Then if you do some thermal treatment, then you can have this. Hey, it looks like same. These balls. Okay. Then using this the ball, you can have carbon nanotube. And then indeed, we observe this. Here is a metal particle, and the single carbon nanotube growing through the metal particle. So what you have learned here, if you have the thicker, bigger the metal particle, you have a thicker tube. If you're a small one, then you may have the small size of carbon nanotube. All right. So this is okay. And this is the growth of carbon nanotube using a substrate, the silicon. Okay, so that's good. And then of course, because this is the 3 millimeter high, and then it's fantastic, the long the carbon nanotube single wall. So that's good for the publication in the science or nature. Because this is the first time to grow such a long the massive growth of carbon nanotube. But if you go to the industry with this the result, they immediately ask you, please bring us the 1 kilogram of this material. Okay, so then I tell you, what we need is this. If you are doing the sort of pure science, that's okay. But if you are doing something applications, the problem is this: substantial cost down. You have to make it cheaper, okay? And then efficiently, you have produced a ton of carbon nanotube, but it's still long way to go. So, but we had the last 5, 6 years, okay. And for instance, oops. At the beginning, this is a substrate. It's just a 2 by 2 centimeter the silicon. Silicon substrate is very expensive, okay? So you cannot use this to produce a lot. Then as the substrate, the silicon, oh, so sorry, size is 2 by 2. Then the silicon is expensive. The substrate is silicon. And the carrier gas, when you grow the carbon nanotube in the gas, usually we have the helium gas, okay? So again, all these are very expensive. So what we had done the last 5, 6 years, we replaced this the size to A4 size, so quite a big size now. And then the expensive silicon substrate is replaced with the stainless steel foil, okay, much cheaper. Then of course we had nitrogen gas for this the periodic reactions. Okay, so but the next one is our 6 years effort. Before that I had a possible application of carbon nanotube. Carbon nanotube, already we know the very interesting, promising the properties, semiconductive, flexible electronic conductors, the FED, field emission, large surface area. It's nice, and we have a lot of application using these very interesting properties. But still, always come back to this mass production of material. So large-scale production of CNT for industrial application. And then that's why I meant. See, I told you this one. Okay, using this technique. So in 10 years ago, we had this reactors, silicon wafer, oven. But this is oven, and then the catalyst. And then we have this the nanotube grown on the silicon substrate. Now I said we are using the stainless steel foil, but it's no one. Still we have cut, and then we coat it with catalyst, and then we put them into this the belt conveyor type the reactor. So it's automatic pizza the makers, okay? And if you had the pizza, go into the other side, you have already the pizza done. Okay, so it's automatic. And this is still the 10 by 10 centimeter size. But this is just completed this year, beginning of this year, January. Sorry, the length is the 12 meters. Then the substrate, 50 by 50 centimeters, stainless steel foil, cheaper. Then the efficiency or the 205, we had 5 gram, only 5 gram, okay, per day. Then the 207, 25, this year, 600 gram per day still. So our competitor, our sort of enemy, is activated carbon. Okay, activated carbon is a pretty cheap material, so you have to compete with this activated carbon. We know, we know this carbon nanotube has very, very excellent properties, but just price is so expensive. That's why the people cannot use this expensive material. But this is the effort. Okay, so yeah, this is very. If you slide later, I tell you very, very surprising the application of carbon nanotube. Okay, so as grown carbon nanotube goes like that, the mixture of two types: semiconducting tubes and the metallic tubes. Okay, so yeah, so now we can separate them out, separate the metal or the semiconductive tube. The separation is many people already successful to separate the carbon nanotube. Then if you paint on the metallic tube, then on the transparent the plastic film, you can have the flexible electrodes. Then also if we use the semiconductive tube, and you can make a transistor. Oh, before that, okay. Once again, I should emphasize this point. Okay, this is the FET, the transistor, using the single filament, the carbon nanotube, semiconductive tube. This one, the guy did this first experiment that had the Nature or the Science paper, I forgot. So once again, that's good for the good publication, but nothing to the industry. Okay, that's the point. So we have to work on this. Right. So now we can have this the transistor, thin-film transistor. Instead of using just a single filament of carbon nanotube, but we have a collective material. Then we can use the simple, the printable inkjet type the deposition or devices. Okay, then this is very surprising. Okay, maybe you're shocked. This is not our work, not the Japanese work. This is the Chinese work. Okay, Shoshan Fan is the Tsinghua University in Beijing, Peking, the professor in applied physics. Then he had very nice the way to prepare the oriented single carbon nanotube or multiple carbon nanotube. So this is the 8 inches wafer, but then the nanotubes are grown on that. But they don't need the kilogram of carbon nanotube. This is sufficient. Okay. So what they did is this is moving. Okay. So 8 inches. Then this one is kind of the belt. You can pull from this deposited carbon nanotube, continuously. So you can do. So like if you go to the weaving, making a texture, then next one is the right. So this is used for the touch screen, the touch panel for the smartphone. This month or yes, will be on the market, the Japanese market. So this one, smartphone. So the carbon nanotubes are already used. So this is the Tenjin, and in China, this Shoshan Fan sensei, he has the factories in Tenjin, and then they're making this. And the product is distributed by another Chinese enterprise called Foxconn, Foxxonn. Foxconn. This is the Taiwanese, this company are producing the 40% of all the iPhones Apple product. So I'm working for the NEC a little bit. So they are much, much bigger now. So right. And the most surprisingly, the social sciences, they said replacing ITO, the indium tin oxide, with pure carbon, because this is, do you know what it means? This is said by Chinese scientists. And then we Japanese, we started the substitution of ITO material. Then we got money for the graphene, for the touch panel application. They don't need worried about the shortage of this rare metal, because China producing the whole rare metal, but they are already working on substitution of rare metal material, and they completed this one, and then the markets are already. So he promised me to give me the 2 iPhones, this one, maybe within 2 weeks or so. To me, it's kind of sad to Japanese, but it's okay. And to me, because we started this carbon nanotube here in Japan, and then there's someone may use this interesting material, and then they put them into market. So that's what I thought, because a month ago, the Apple announced they are going to have the iPhone 5. Okay, then he said, Shoshan Foundation said maybe our product might be used iPhone 5, but Apple didn't take. So according to them, him, Apple is very cautious, because once you have some defect, the device, and then it's a big problem. So this time they don't use. But iPhone, the smartphone, or I don't know, this Kyocera, or other makers definitely use this nanotube. Okay, so much about the smartphone touchscreen is made by CNT, and also made in China. Okay, let me change the subject. Okay, so I got this Bunkakunsho, the Order of Culture. Okay, so then the next one is important to me. Many people in our science or engineering community, IIJIMA, he's the inventor of the discoverer of carbon nanotube, but I don't like it, because carbon nanotube was discovered 1991. So my research career already I had 30 years before that. So people don't know what I have been doing. Okay. So that's what I will tell you. And this Bunkakunsho, and then the citation said, I don't know if this is good English or not. Anyway, so the top one, oh, okay. So sorry, I should say the English. The development of HRTEM stands for high resolution transmission electron microscopy method for the material science, and the discovery of carbon nanotube. So first part, I like it very much, because they recognized what I have done before. All right, so now the science starts with seeing carefully, seeing things carefully. Okay, so this is Kagoshima, Kyushu, and volcano, and this is interesting. And one Japanese physicist had the pictures where is the magma of this mountain, the volcanic mountain. So this particle physicist, experimentalist, oops, oh no, 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 go back. All right. So he used the person Tanaka. He used the muon. This is the everywhere. Okay. So the elemental particle. He had the. This is my interpretation. It's a little bit complicated, but I think what he did like that. He prepared the detector because muons are flying everywhere, every direction. So then if you arrange these two detectors, something like that, then I think the analyzing this sort of information, and that he had this imaging. So what I'm going to say is that this is one of things to see. Okay, so I show you more example. Next one is this is for high school boy, okay, high school student. Blue color, beautiful. Then if you stop there, if you don't go further, then you should quit the scientist. Okay, so if you you got interest more, then let me see. Yeah. This is some part of the wing here, butterfly wing. So the problem is why we have the blue color. So, but this is already we have the scale of this the Limpun scale, but the still not good enough. And then we not me, a friend of mine did this one. So next one is the scanning microscope image of the wing, the scale. Then the size is the let me see, like that, almost the size of our hair. So several tens of micron. Then we have the periodic arrangement. So maybe if you go to high school physics, then there might be some kind of diffraction. Then I try to connect to the blue color. Didn't work for this because this periodicity is too big. Then the friend of mine cut the one of these scale. So this is surface structure. Then you have the beautiful periodic structures. So then if you come to this point, then we can understand. Right, the natural light. Then we have the many wavelengths because some of these grating give us a particular reflection. So then we could understand this, the secret of blue color. If you stop there, you are still no hope. So my next question is this. This is the English word, camouflage. Okay, so this the butterfly or something, moth or something. It's hiding. Okay, so camouflage. There is another insect hiding here. Okay, it's very well done. So a problem is the developmental biology. Why we have this the interesting structure in a morpho butterfly wing, right? So the question is how these structures have been evolved. Now I'm going to the biology a little bit, okay? So to explain this, the progress, evolution, you have to go to the Darwin. So evolution, why this butterfly developed these beautiful structures. So I'm very interested in this. Then of course we have to go to this the DNA because secrets are all in DNA. So that's we should drag. But this is not my field, so I stopped there. But maybe young scientists started to do this. All right, so structure of DNA solved by X-ray. Still, I'm talking about seeing things, okay? Miru koto. The structure of DNA solved by X-ray. Then there are this beautiful lady, Rosalind Franklin. She had this X-ray diffraction pattern. So this is the beginning of the DNA structure, okay? So this is simple, the arranged X-ray diffraction pattern. So actually she's a student of Barnard, but actually it's those who got the Nobel Prize is not this group, but the Watson, the others. Anyway, so this is very important. Then who invented the X-ray? So if you go up, sorry, some Japanese. I was fixing this Japanese one. So this is Max Pong Laue. He did first experiment, and then have crystal, and then they sent the X-ray, and then behind this sample, they recorded this X-ray diffraction pattern. Then solving this pattern, and got the what atomic arrangement in the crystal. All right, so now how do we see things? So sorry, I can't translate the entire one. I was working yesterday. Using light, we can see the butterfly scale, the rimpun, and then of course star. Then the X-ray, we can have the DNA, the X-ray, the telescope, and then we can see the universe, ultrasonic wave, the liver, the body. So muon, I show you this volcano, and then electron. Then by electron, I saw the carbon nanotube. Then the needle, if you're using the STM, then so all these technique to see something. So I think this is very important. That's my point. In science or engineering, you have to watch or observe. This is very important. Okay, so then I go this third subject. My teachers who told me the importance of seeing. Okay, frequently asked the question, how did you find the carbon nanotube? My answer is accidental, the serendipity, guzen. But then I said this is somewhat logical, the discovery. It's not completely the accidental. So that's to convince you this, I have to say more about my background. All right, so I do some. Electron microscope, comparing with the optical microscope and the electron microscope. Of course, we can see more detail. Then material science research by, okay, to explain this is important. How did I discover the carbon nanotube? Okay, so it was discovered in 1991. Then I had the picture. Okay, after this. So sorry, this is not English yet. This is diamond. I have been working on the nucleation of diamond film. And then in 1991, next year also, I accidentally find the carbon nanotube and the carbon nanohorns and microscopy. Okay, so this is NEC. When I was at NEC, the carbon nanotube found. This is Meijo University right now, and AIST. Okay, so those 25 or 30 years, the background of my research activity is important to explain how I got accidentally the carbon nanotube. So I tell you later. Okay, so this is one of the teachers when I went to the graduate school in Sendai. So he actually taught me the electron microscope. So far, after that point, I never seen the electron microscope in a graduate student, but he went to there. I saw the first time the electron microscope. Then I got really interested in the electron microscope. Okay, so this is my part of thesis. Master course. This is actually described as silver whisker. Okay, the silver whisker. This is needle-like the filamental the metal, FCC metal. Okay, so next one is see you know similarity. These two the objects are the similar sort of morphology. Okay. So this is I go back because the structure of this silver filament is not a simple the FCC silver metal crystal. It has an interesting the defect twinning, and that's why they can grow so anisotropically in one direction. Usually, you can have the crystal growth of metal. You have sort of bulky material. So I know how to know the crystal structure using electron microscope, or such a elongated fiber the material. So then after 30 years, when I had this the object. Immediately, I went back to 30 years in my student time. Then they utilized this analysis technique. Then a few days later, already I know what atomic structure and the graphitic structure and the spherical the cross section. Anyway, so this is number one. Let me see. Okay. Maybe I'd add this one because of you. When I had this the nanotube pictures, many people claimed, no, you are not the first guy to find the carbon nanotube. The other people already reported. Okay, so the oldest one is 1953. It was published in the Soviet Union at that time. They had similar electron micrograph. And they said this is first time to see the carbon nanotube, but this is important. What they show us is it's written in Russian, so not many people can understand. Anyway, so they don't show this the important scientific data. This is the electron diffraction pattern. So if you analyze this electron diffraction pattern of this single filament, it's actually what I did in my graduate student. So then I can say the object really has the graphitic structure and the diameter. So this is much the clear scientific presentation. So without this, maybe what you had is a carbon nanotube, but something else. So since we were doing the science, we have to show the nice scientific evidence. So please, if you find something interesting, you showed a lot of the evidence to prove your or to convince the other guy, because maybe they claim you. Anyway, so okay, so and then this is another example. This is not the carbon. This is asbestos. Okay, so this is filament. It's very much like a carbon nanotube, multiple carbon nanotube. So when I was a student, the boss, semi-boss, Jo Kyoju, assistant professor, has been working on this the asbestos fibers, okay, using electron microscope. So the morphology is exactly same as the carbon nanotube. Then of course, he was observing this electron diffraction pattern to know the more detailed atomic structure. So then I remember all this. Then when I told you already, when I saw this carbon nanotube elongated the structure, immediately I come back to this one and the silver filament. So it's very useful. I tell you a conclusion, okay, later. So then I dreaming of seeing atoms, and I get out of Japan in 1970. I went to the United States. This is okay, progressing in TM resolution as time goes. 2000, when I went to the Arizona State University in 1970, resolution is something like a 0.4, 0.3, 0.4 nanometers. So the instrument is not good enough to see the individual atoms, but I did similar things. Metallurgy, okay, this is most important. Okay, so this is the pictures from Kittel, the solid state physics textbook, and then you see this picture in some editions. Anyway, so then this is conventional at that time, the 1960, before 1970. So this is very useful, so that all metallurgy had the golden time. The microscope really worked. Then I went to the United States, and then I had these pictures. This is what I call the high-resolution micrograph. First time, we showed the atomic, the individual atom positioned in the crystal. So this one is the 1971, okay? So I was quite lucky. And this technique, what we call the high-resolution microscopy, is now we commonly used. And from now, I showed many pictures. Okay, so this is the very beginning. Yeah, still I was young. Then maybe, yeah, this is the graphene layer sheet, okay? The tungsten atoms on graphene film. So I deposited this heavy metal, because heavy metal is more visible in electron wave scattering factor, more scattering. Okay, so maybe one of these small dark dots might be individual atoms. So I said this is the first time to see the atoms in electron microscope, transmission microscope actually. And then this is second one. I missed a Nobel Prize from this one. I published this one in 1980, and this is what we call the onion type graphite, okay, spherical structure, and then this central regions here. That is nearly the same as the C60 molecule, okay? So then furthermore, well, I said in my paper, I said in appendix, there must always be 12 pentagons. But I didn't have these pictures, but I added this one. In other words, if I was smart enough, maybe I reached to this one. But I didn't. I was maybe stupid. Anyway, so but later on, the Harry Croton and Dick Smalley, the boss came to me in Arizona, the scuba, because when they had this first paper in Nature, not many people believed their work, because they showed nice the mass spectrum, C60, big peak. And then that's all. So there is no scientific presentation. Maybe this is a chain of carbon atoms, 60 of them, or maybe something the ball. Nothing about the structure. And the great thing of them is they had speculated this model, okay? This 60 the carbon atom structures. And that was the greatest part of the work. But until that, only these pictures, my picture is their evidence, okay? There might be spherical, the structure. And then because of that, the Kuroto came to me in 1989. Okay. Then the next year, 1990, then we had the mass production of C60, and then a group of Berkeley, the people, did the X-ray crystallography using this fluorine crystal. Then they proved these structures. So then Kuroto, the Smori were happy with this. Then my picture is finished. Okay, so still I'm talking about the microscopy, and because I said before carbon nanotube, not many people don't realize what I have done. So one of this contribution to mineralogy. So this is the cover pictures of my electron micrograph of mineral, and I worked with the many mineralogists now, mostly in the United States. So this is one of them. And since we started the high resolution microscopy, then this new technique is very useful in many areas. Mineralogists, so they came to me. Then we started work. Okay, so then they come back after 3 years to stay in the States. They joined the first JST project. Okay, I mean, it's too much. So this is the fourth or third or fourth grade teacher, Professor Ueda. And so come back to Japan, I worked with his group, his project. And then this is one of the old pictures. Many times I've been showing this one. Yeah, this is the gold particle, and then they are moving. And then I think this gold particle is somehow coming back right now. So this is original. Then the structures are all the time changing. This is the cube octahedron, conventional FCC crystal, but this is icosahedron phase. Then what they call the structural, the instability they observed. Anyway, then of course if you measure the melting point for that nanoclusters, nano crystal. At that time, there's no word nanocrystal. We say the outer fine particle. Anyways, the melting temperature is going to be the lowered as you decrease the diameter. This is the 20 angstrom, 2 nanometers, and then consisting of about 500 gold atoms. Okay. Actually, with this, I got a big Japanese prize. It's called the Nishina Kinensho. It's the highest prize in Physical Society of Japan. Then the story didn't finish yet. So here is the person Haruta. And then he's now the godfather of gold catalyst. And then again, he had the great difficulties when he had this great discovery of gold catalyst. Not many people believe that he's gold catalyst. Then I had this the gold the observation microscope. So he immediately came to me, Nagoya. Then he brought his gold catalyst, and then we worked. I worked. I think his picture. This is gold, and this is the carbon monoxide, the oxidation. Okay. Anyway, so Now, then discovery of carbon nanotube. So the conclusion. This is another picture of carbon nanotube. Okay, so how I got how did I discover this carbon nanotube? To convince you, I showed the old work. So I had already a lot of experience with instrumentation, microscopy, and also material, carbonaceous material. All these helped me a lot to find this. All right, so then I come back to the same slide again. So I think that's why I wanted to say this. It's not an accidental discovery, but quite a logical discovery. Okay. Material science, all right. So I showed you this one. Then above that, or this is Japanese, sorry. Silver filament, and then I did high resolution microscopy in Arizona. Did this at Arizona State University, and also partially I stayed sometime in Cambridge. Then observing single atoms, and also I did work a lot of imaging of the amorphous carbon. Okay, so all this done during 1970 to 80s. So here 91 is a nanotube year. Okay. But here, then I worked the gold catalyst. And these are all the nano science, okay, nano material. So the background helped me a lot to find this carbon nanotube. So do you now convinced? All right. So I think this is something. Because of that, I had the prize or something. Okay, this is Benjamin Franklin. That's for all the carbon nanotube. Okay, but I saw the Nishina Memorial Prize. That's not carbon. The Warren Prize. That's from the American Chemical Society. American Crystallography Society, so the Barton Warren show prize. Anyway, this is Barton Prize for Nanoscience 2007, and then because these two, this year's Nobel laureate in biology. This is 10,000. No, the $500,000. Okay, so this is the Kavli Prize, right? Okay. So how do you get the accidental the chance? Okay. So how do you get the fortune? So I said you should move. Don't stay in the Kyushu University. Go to the other university. Okay, abroad, anywhere. So that means then you get you meet the nice teachers. I had a full teachers, excellent teachers. Okay, so if you stay in the Kyushu University until end, you have only one teachers. So, and then also, if you move, then you have more probability to meet the new things, new teachers. So particularly Japanese don't move much. Okay, and youngsters don't like to go abroad, and so then the potential you have to train with high how do you say it, the motivation or something. All right, so serendipity, it's the, okay. This is from the book. All these, the dynamite, X-ray, radiation, Teflon, Big Bang, penicillins, the neutrino by Koshio, not Koshiba sensei, Nobel laureate, Mordi, protein mass spectrometer, Tanaka Koichi-san, and Shirakawa-sensei conducted polymer. All these great discoveries are done by chance. Okay, the no logic. They are doing something. And beside this, they had great discovery. So this is very encouraged us. Okay, maybe you're pretty smart, but to me, I can do some discover new thing. Okay, if you want to be a realist, the theoretician, Masukawa sensei, Kobayashi sensei. Forget about this to be a theoretician. Okay, so these are all experimentalists. Experiment is much easier. You can do it, I can do it. Okay, so then we have the chance to find the interesting. And that's my statement. And then of course, yeah. In the field of the observation, chance only favors those minds which have been prepared. This is a great word, pasteur. Originally it's French, but yeah, this English translated. Anyway, so particularly in these countries, in Japan, maybe fortunately, unfortunately, the first three Nobel laureates, all the physicists, theoreticians, okay? Yuga sensei, the Tomonaga sensei, the Fukui sensei. So these I cannot go these areas. Maybe some of you can go, but that means the science is quite high in a good place. Okay, we are here. Only genius go to there. They can do the top the work in the theoretical. This year, we had a couple of years ago, we had the Kobayashi sensei, Masukawa sensei. They are really genius, okay? So you should go that field, okay? And you go this experimental area. Anyway, so I think with this I should finish. Right, so this is a condition to find the something, the curiosity. And then you have to really train your technique. I trained the microscopy. I used to say I may be the best in the world to use the microscope. So I can do a lot of things. If I have the same instrument, then you started this one. I started this one. So same instrument. I can get more information. So that's you have to know everything here. Okay, so you buy the instrument from the producer, then stick your specimen in microscope and started to collect the data. But that everybody can do. But you have to show something new. So to do this, you have to really train your technique. All right, so concept observations. You have sort of inspired sort of eyes. And so if you go to antique, and there may be fake, nisemono, then there might be the real one. But you have to judge. So how to train to judge the. So I don't know the answers, but you have to see many things. You have to have a lot of experience. All right, knowledge and the chance. Yeah. Okay, I think with this, I should stop my talk. The last one said about TM, but you can find in the textbook or published the material. So I said what is carbon nanotube, including the applications. That I tried to show the important things to do. Science started with seeing carefully. My teacher who told me the TM, discovery of carbon nanotube, I didn't have time to show this one. Okay, with this, thank you very much for attention. Thank you.